Hello, welcome to Numerical Ship and Offshore Hydrodynamics. Today is the lecture 51. Today we are going to discuss about the development of this of the numerical code of the time domain panel method. Mostly we are going to discuss about the linear part of it. Uh, I would say that this is not the other, compared to other code that we discuss in this course. I would say this is the most difficult code among all. So, it may not be possible to address all sort of things, but however, we are going to discuss some key aspect of it. So, this is the keyword that you have to use to get this lecture. Now, let us start. Now, here as I said that in this class we are only discuss some key aspect, and also we realize that we have at this point after 50 classes at least you have some idea how to generate the matrix, how to convert the integral equation into the system of linear algebraic equations, how to solve the algebraic equations. So, I assume that at this point you know all these things. You may not be an expert, but at least you got the idea. Now, in any code definitely you have to have some kind of input, otherwise you cannot start. Now, here the inputs are actually the geometry, the ship geometry, or you can say the paneling, and also the mass properties, that means the mass of the body and then the radius of gyration, the kxx, the kyy, those are the kzz, these all are the inputs. And also you have to give the input that which time period you want to give, so that you can get the response. So, the time period, let us say it is a 10 second or 15 second, whatever, and also you need to give the total simulation time. So, it is you can call this T max. So, it is how much second, is it 20 second or 100,000 second or whatever, right. So, this is the more general input that it is required to run this code. However, if you use some kind of software like MaxSurf or other thing, some other kind of inputs also they prepare for you. For example, the coefficient C33, rho G AWP. So, this AWP you can get from some software like MaxSurf probably provide this, the surface area, and also the volume. So, all these things that also it is possible to get from the other external sources, and you can use this as your input, like or maybe this the C55 and the C44, everything actually you can get from some different softwares. So, this is not the very big deal, even if you have, it is good. If you do not have, we already discussed before that how to get this hydrostatic coefficient in our code, I mean using the time domain panel method. The more interesting part is that from these inputs, let us have this input, then how to start the code, like how we can thought of. Now, here one part is the time independent part. Which part is the time independent part? Definitely we are going to discuss. So, this after getting this input, we need to understand that some part is the time independent part, and this time independent part we have to calculate or compute before you start the original coding. So, this original code definitely the time dependent part, right. It has to be there because it is a time domain simulation. So, definitely the major part is the time dependent part, but however, there is a lot of things that you need to calculate before you start the coding, the original time part. So, now what are the things? So, as I said, the basic hydrostatic coefficient you need to figure out, like that means you have to figure out that that coefficient, that C33 or maybe C35 or C53, all these things, right. And then the second, which is the important thing, you have to find out you need to do the integration of the Rankine part of the Green's function. Now, if you remember this Rankine part, or you can call it as Z0, this is actually this 1 plus R plus 1 plus R dash. So, plus or minus anything, but this is the time independent part. So, we have to use this, I mean we have to calculate this integral, and we have to store it before we start the time dependent part. Now, in time dependent part, we have the dynamic part of the Green's function. So, it is GF. So, this dynamic part of the Green's function we need to use, we have to evaluate, and actually we have to get this, that convolution term. So, what is the convolution term? This is one of the critical thing or complex things that actually they are in this code, and also we have to find out the pressure, the forces, the displacement, the velocity. So, this is the main thing, right. So, now in the next slide we have to figure out that how we can do this time independent, that the Rankine part of the Green's function, how we can do the integration. Now, this is the classical or that integral equation. Of course, this is for the 0 speed. Why are using the 0 speed? Because the forward speed only we have one term to discuss, but here this second bracket is missing anyway. Now, here you can see that this part actually we are talking about. Now, in this integral we have two parts. Now, if you look at this part is integration from 0 to t. Now, to be honest, it is t is not the present time step, rather it is, we can call a t minus in the delta t, till the previous time steps. Okay. But this part is actually the time independent part, and also in the next equation, which is phi t into this, here also you can have this Z0 term, which is again the time independent. Now, you might say why I call this as time independent, because in this integration you have S0 t, right. You also have the S0 t. So, you might asking like, so that S0 is depending on the time. So, therefore, at each time step the S0 is changing. If S0 is changing, then how this integration term is time independent, right. We are going to answer this question. But before that, actually if you look at this carefully, what I did actually, I write this the way we are going to solve the integral equation, or the way we are going to write the code. However, when I develop the theory, you know that we write this equation first, we give this equation number 1 and I give this equation number 2, and we say that here in this equation number 1 I have this unknown is sigma, and then the phi, both is my unknown, and then I differentiate with respect to n. So, I will get this equation number 2, and in this equation number 2 is everything is known to me apart from the fact that sigma is unknown to me. So, therefore, I solve this sigma first, and then actually apply this sigma in the equation 1 to get the phi, right. This is the statement, right. So, here since we understand that first we have to solve this, the equation number 2, if I write it 2. So, that is why I write this equation in the top. Now, here I have this part, I claim this part, and from here this part is time independent. So, why I am telling so? Now, actually these two part it is only time independent when you do the linear analysis. Why? Because in linear analysis the S0t, which is the body surface, the weighted surface, is not function of time. If you remember that what we say that that level, I mean level 1, level 2, level 3, level 4, all level we discuss. Now, in the level 1, the thing that we discuss is, in fact, in level 2 also, this weighted surface does not change with respect to time. Now, that means this paneling actually does not change with respect to time. Only in case of a level 3 or in case of a level 4, that time only the geometry, the underwater geometry, it is changing with respect to time. So you know, we are not going to discuss about the nonlinear part. It will take you know, another level. Let us first understand at least the linear level. In this in linear level, this weighted surface does not change with respect to time. So, therefore, you know, this integration and this integration we can do before actually we start you know, doing the dynamic part of the course. So, this is you have to do one time. Okay. And now, after doing this, we need to store the matrix A, this part, and we have to store the store it in matrix B for the second part. Okay. Now, what actually we need, we are having in this matrix A, let us see. Now, in this expression, this left hand side, this part is nothing but the velocity, which is known to me, and we can call this Vn, right. So, this velocity component definitely, you know, I am taking that in the right hand side, right. Now, if I look at this part here, this actually del G del N, that coefficient actually coming into the A matrix, right. Now, this you know already. So, you understand very well why I am writing this. It is simply, if you remember this panel method code initially, we know that we call A as the influence matrix. So, how we are going to write this A matrix, we know this, right. So, remaining part, which is this part, now people will think that why actually this A matrix, why the contribution from the second integral is not included in the matrix A. You know, that is the fundamental doubt that everybody is having when they solve this problem. They say that okay, no problem, I know that this part actually is the you know, the independent part, and this sigma also is there. So, this is the influence matrix A sigma. People know this very well. Okay, yes, I have no problem with this. But here, why actually in this A matrix, why I am taking only the contribution from this part, why I am not taking the contribution from this second part? So, we are going to answer this question. However, at this moment, let us go with this, okay, to construct, at least construct the matrix, the left hand side. We are taking this part here, and then we are taking this side over here, and we are taking this part over here. Now, since it is, we have this minus 4 pi is, you know, multiplied throughout. So, this minus 4 pi multiply over here and I take this the right hand side. So, it is 4 pi into V n is here, okay, and we are just keeping it as it is here. Now, I am going to answer the question that why actually I do not take the contribution of this into the A matrix. Now, if you look at this carefully, what is this sigma and what is this sigma? Okay. Now, here it may be confusing. So, normally we take this, it is actually the tau and this is actually the t. Now, what is the difference between the t and the tau? Now, in time scale, let us say I am evaluating at, let us say t is equal to 10. So, now this sigma actually if I look at it, it is sigma the q at the time step 10. Now, these sigmas are basically it is sigma of q starting from 0. Okay, let me write in more bigger way. Then we have the sigma at q at time let us take 1 and then it actually end of the sigma of the same point q at point 9. So, that means these sigmas are basically the it is the strength of the dipole of the previous time steps. This sigma is not the strength of the dipole of the present time step, which actually I am going to figure out from this expression. I think that is fair. I mean, it is makes sense, right? So, that is why we do not keep this sigma into the left hand side, because this sigma are the sigmas of the past time. Now, this sigma started at 0 and this sigma is ends at t minus delta t. So, I know the value of this sigma, is it not? Now, when I solve the time step 10 sigma at time step 10, so I know that by that time I know sigma at time step 0, I know that sigma at time step 1, 2, 3, 4, 5, 6, 7, 8, 9 and then. So, therefore, in this second expression all the parameter is known to me, because sigma is known to me, because I know the sigma from 0 to 9 time step. I do not know the sigma at the 10th time step. So, that is why I wrote I take this entire thing in the left hand side. However, I know the remaining sigmas. So, since I know the remaining sigma, this sigma should not be the part of the matrix A, rather it should be the part of this matrix, right. Okay. Fair enough. Now, let us see about this summation thing. Now, here it is actually I written is a matrix form. Now, in A matrix what is there? This A matrix if I write it somewhere, I do not know where I should write here, let me write here. This A matrix, if you write this A matrix, I mean what is the element of the A matrix? Now, if I consider, if I try to write the element of the A matrix, what is the element? Now, it is A11, A12, let us take A1n into sigma 1, sigma 2 into sigma n. This is the thing, right. Now, what is A11? Now, you know very well, right, what is A11? I mean, you should know A11, the first term is referred to my source point, and the second one referred the first one is referred to the field point, and the second one refers to the source point. So, what is that? Now, I just again just for to remind you, now if I have this paneling, if I take this number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, then if I put this source point P at time step t, it should be the field point T is an arbitrary point. But if I take this as the first panel, that is the idea of the panel method, right. So, then corresponding influence coefficient becomes A11. So, therefore, this A11 is nothing but it is, in the panel 1, in case of a panel 1, right, we have the del G, I mean it is the source point now also 1 and the field point also 1, which is del n, and now it is on the panel P. Now, remember there is a difference between the previous formulation, where this normal we are taking at the source point, here we are taking at the field point, del G del n P into ds1, that is my A11, right. So, now when I talked about that influence matrix is complete, it means that I am taking all the field point in the left hand side, right, because A matrix have all the element, right. A matrix have this AN1, AN2 and then ANN, that element also there in the A matrix, right. So, in case of this A matrix, I am sure, I mean I know that I take this all this n, this is a n cross n matrix, right. So, I am taking all this panel. So, let us take if the total number of panel is n. So, I am taking all the field point in the left hand side. So, that same thing I need to do for the right hand side also, right. So, that is why I am having this summation sign, because this right hand side is nothing but the column matrix. This right hand side should be the column matrix, right. So, then if I take n, now okay, I just make it NP. So, it should be, let me correct it, it should be NP cross NP matrix, right, and I is going from 1 to NP. Now, this should be the column matrix, right, it should be the NP cross 1, right, I am just writing over the top. This should be the NP cross 1. So, now each summation is not adding row wise, no, this adding actually the column wise. So, if I take the first point, then actually if I write this, we have the less space over here. So, the only thing I can use here in the right hand side corner. So, I am always deleting thing anyway. Now, when I just take I is equal to 1, then I can get only the column matrix. Okay. So, here now if I do that, this I is equal to 1, then what I get? I get this integration of sigma. So, it is so this integration over this body S0. However, this del n p is 1 and it is 1 comma q comma t minus tau into ds. So, this is how actually we should do that. Okay. Fine. So, now this one actually when I take I is equal to 1. So, I take one number. So, then if I take I is equal to 2, so then actually in I1 I take one number, it can be 1. So, if I take I is equal to 2, that means if I put my field point in, let us say, the second point, it is, let us say 1, this is 2, this is 3, 4, 5, 6, 2, then I get B 2, in that way it is going. Okay. Now, let me this is the most critical part of this thing, which is called the convolution integration. So, now here this is how actually I can write the convolution integral part. Now, what I am going to do is this S0t is nothing but my body surface, and this is the paneling. So, what I can do is, this is now I know that this is the NP number of panel. So, therefore, this integration part I just write in a summation term, and this part also, this integration is from 0 to t, that also I can write as a summation term, right. So, for this integration I have one summation, and then from integrating this over, now this is the difference between I and j, right. I for the field point, but the j for the source panels, right. So, therefore, this integration, this S0t actually I can split in the small number of panel, and then from each panel actually I am going to do this integration. Now, this is very clear. If you know the Wamit type solution, that time also we did that, right. So, there also we split this surface in number of panels, and each panel locally I am doing the integration, right. Now, the part is the interesting part is how do the convolution integral. I know now this part I am not going to discuss here, because as I said that let us keep this part right now. Maybe at the end of this course I can provide you the entire coding in MATLAB coding of this Green's function. Let us now only formulate, suppose you have this Green's function code, how to, still it is very difficult to write this the other code. Now, here how actually you deal with this convolution part of it. Now, you see it is actually not that easy to realize. Okay. So, in order to realize it, we need to understand this picture. Now, here always this p is referring to the time step t, and then this q is referring to the time step tau. So, q is the point on the previous time steps, whereas the p is the point on the present time step. That is also you need to consider. Now, see here, now for a fixed pt, like now suppose you fixing your eye, as I said, you fixing your eye, and then you are actually fixing your j also for a space coordinate, but you can vary. Now, this q point is, it has two variable, one it is vary over space. So, it is run over j, also it varies over time, it is run over tau. Now, I am only varying the tau, so I am fixing the I and j. For example, now let us try to do this integration. Now, suppose I am having my panel P in the panel number 1. Now, I am having the source point Q at the panel number 2. So, I am fixing 1, 2. Now, although you fix your 1, 2, still you see you have to do. Now, let us take that your P, the T is about the 10 second. So, now what you need to do, you see it is not, that is why it is so complex. You have to do that Q for the panel 2, and not only for the, you have to start it with a point at t equal to 0, then you have to take the point at 2 equal to 1, and so on till the q point at 2, 9. So, you have to take all this point. Now, in time scale, so now in time scale also you see you have so many points. It is in a space scale, you have np number of point. Now, and each np, each j, again you are having a time scale, and that is why you have so many complications here. You have first overall you have I, which is run over the field point. Now, you have the j, now which is a run over the source point. Now, this if you fix your j also, then it runs over from 0 to t minus delta t. Now, here as I said, I fix my p equal to, let us say, the first panel and 10th second. So, again I fix my q. Now, let us it is in the space coordinate the second panel. However, the time coordinate should run from 0 to 9 second. So, then actually I have to compute that what is the value for Gn at so we have to figure out that Gn at q equal to 2 and tau equal to 0. Then you have the next point, when that it is this point is basically when q equal to 2 comma 1, this point corresponding to q equal to 2 comma 2, in that way it is going, right. And then you need to integrate the entire curve under 0 to 2. You need to integrate the entire curve to find out the integration, which is the integration over the time, which is this integration over the time. You see, you have first the space coordinate, each space coordinate like you fixing your j, and then you are running the time scale from 0 to tau minus 1, and then you integrate this, right. So, this actually most critical part of this time domain code. I really I try my best to give you some essence of it, but still you need to do a lot, you need to think a lot to write the algorithm for this particular convolution integral part. However, once you do that, okay, how we simplify this, let me also, I forget this, let me quickly I will tell you that here at each time step actually you need to repeat this, right. Like what I say that when t is equal to 10, you need to do from 0 to 9. Now, when t equal to 11, you need to do from 0 to 10. Now, when t equal to 12, again you need to do from 0 to 11, is it not? So, all the time actually the convolution starts from 0 here and it goes up to the t minus delta t, right. Now, this is very time consuming. So, how we simplify this as follows. Now, what actually we are doing, it may not be that accurate, but still it is fine. Now, I just split it into the time scale, let us say it is your t equal to 11. So, now I know the value, like let us start from the 0. So, 0 we do not have the memory effect, so we are not going to do anything. Now, when this t is equal to 1, we have this integral, right. So, we store it, we store this value. Now, when you do t is equal to 2, we need to start from 0, but we have already stored this value, we are only integrating this one, and then we add this plus this. However, frankly speaking, you have to take from this, because you have to take g, which is p, which is q, you have to do the t minus tau. So, it is, let us say 2 minus 0, and then you have to do g p q 2 minus 1, that also need to do. But we simplify this, we only store this value, and this value we can get from the previous data that we are storing, and we can simply keep adding. So, we really do not do this integration when t equal to 10, we are not going to do from 0 to 9, we only do the integration from 9 to 10, and then remaining thing we simply add with the previous thing. So, this simplification we do, and it works nicely. However, if you want to really have a robust and very high computing machine, you can do from the 0 to the t minus delta t all the time. Now, when you do all this exercise, and then these terms also now you can write in terms of a column matrix B, right. Like I just discussed for I is equal to 1 uh, right now. The if you repeat for I equal to 2, 3, 4, 5, 6, do all this convolution integration everything, then each time you are getting B 1, B 2, B 3, B 4 a column matrix, and finally you are having the B, and once you have this B, then remaining part you know, right. So, this is the critical thing that we discuss. Remaining part we discuss a lot, like other part, like once you know the phi, know how to get the pressure, from the pressure how to get the force, from the force how to get the velocity, and from the velocity how to get the displacement. This part we have discussed many times. So, I am not going to discuss here. At here the whole idea just to give you some kind of light. I really do not know how how I able to do this. It is so complicated, as you know that the writing algorithm is is really complex, but as as I promised at the end of the course, at least the Green's function part in MATLAB code, I have the Green's function that I can provide, and then you can just write this algorithm, and once you done with this algorithm, definitely you can able to write the code, this time domain panel method code. Okay. So, thank you very much. From the next class onwards, we are going to start the hydroelasticity. Thank you.